Hello everybody. In this video I want to talk a little bit about how energy works when we're talking about nutrition and the food that we eat. The first thing we're going to do is introduce two more units of energy. We have the joules that we've seen so far, but then there are these two new units that are really honestly just confusing for no reason. We have calories with a capital C, also sometimes called food calories, and we have calories with a lowercase c, which is really just unfortunate, but we're going to have to deal with them. So our conversion factors here are facts. We're making conversion factors between these units. One big C calorie is equal to 1,000 little c calorie. And one little c calorie is going to equal 4.184 joules. Knowing that, we can see that one big C calorie, one food calorie, is going to equal 4,184 joules, or 4.184 kilojoules. Remember that there is going to be 1,000 joules in 1 kilojoule. That's how we're going to work through our metric system. Now let's talk about our types of food. So there are really pretty much in food only 3 different components, and these are really broad categories that include different kinds of molecules and stuff that we're going to find inside living things that we eat. So there are carbohydrates. These are going to include sugars, grain, fiber, both digestible and non-digestible. Materials, we're going to, and most plant materials are carbohydrates. Next, we're going to have protein. These have a very specific setup. There's bunch of different kinds of proteins, and the majority of animals are going to be made out of protein. And then finally, both plants and animals are going to contain different kinds of fats, and sometimes you'll actually see fats replaced with the word lipids, which kind of extends it to a broader category that'll include like cholesterols and stuff like that in there. So each one of these different kinds of materials is going to have a certain amount of energy associated with it per gram. So a carb that you eat is going to give you 4 food calories per gram. Any protein that you eat and digest is going to give you 4 food calories per gram. And fat, the one that is where we store all our energy, is going to give you 9, almost more than double, food calories per gram. So let's try out a little example problem. Here we have a piece of strawberry pie that has 24 grams of carbohydrates, 6 grams of protein, and 10 grams of fat. How many calories are in this serving of pie? So in this case, what we're going to do is we're going to multiply the mass of each one of the component times its energy content value, and then we're going to sum them all up. So we have 24 grams of carbohydrates. We know that there are 4 food calories per gram. We'll multiply by those. 6 grams of protein times its 4 calories per gram, 10 grams of fat at 9 calories per gram. We can see that when we do this multiplication here, we're going to cancel our gram units, and we're going to be left with calories. So when I do that math, I get 96 calories from the carbohydrates, 24 calories from the protein and 90 calories from the fat. I sum all those together, and my piece of pie has 210 calories. So we just did a problem where we calculated the caloric content of a sample of food by figuring out how much, because we knew how much protein, carbohydrates, and fat were in it. We typically wouldn't have that kind of information, though. Typically, it's not the information that we get. What we would know, though, is how much calories was in a sample by determining it experimentally. And one of the ways that we do this, probably the most common way, is with the technique known as bomb calorimetry. And this is our setup for it. So basically, you have a container that is well insulated. Think of it like a little bucket. Okay. Inside of the bucket, it is filled with a known quantity of water. There is a little stir that comes down in there, stirring the water around, making sure that it has a constant temperature. And we're measuring the temperature with a thermometer. Inside of the water, we put a very strong, usually steel container called a bomb. And inside of the bomb, we charge it up with a whole bunch of oxygen. We just pump it in there and pump it in there. There's a lot of oxygen pressure in there. And then dangling from the lid of the container is a little cup. And inside that cup, we put a little sample of food. And then we have these wires that come down, and they are sticking down into our sample of food. When we pass electricity through those wires, it ignites, because of all the excess oxygen, all of the food and burns it completely. When that happens, the whole container heats up. And when the whole container heats up, it releases heat out into the water. And so the two measurements and it heats the water up. The two measurements that we make are going to be the mass of the food plus the change in temperature before and after we burn the food of the water. Now what happens is we have an equation for the energy that gets released. This energy that's released, which in this case with this setup is equal to a thermodynamic quantity that I just want to introduce to you guys here, called the change in enthalpy, right? So it's a change of enthalpy for the reaction of burning. It's also going to be equal to the heat that was released, okay? And we can calculate it using this equation where we have the mass of the food times C times the change in temperature. Now C here is called specific heat. And what is specific heat? The specific heat is a measure of how much a substance's I should put apostrophe here. How much a substance's temperature rises when energy is applied. Okay? And it is intrinsic to a substance. And that kind of feels intuitive if you think about it, right? If I have a metal cookie sheet, I put it in the oven, it heats up very, very quickly. But when I use the oven mitts to take the cookie sheet out, the oven mitts do not heat up nearly as fast as that metal cookie sheet did. So different substances are going to have a different change in temperature when the same amount of heat is applied to them. Okay? So as specific heat goes up, the amount of temperature change that we are going to see when we apply the same amount of heat is going to go down. Okay, so a high specific heat substance is not going to want to change its temperature, but a low specific heat substance will change its temperature very readily. Okay, and the way that you get the specific heat for a substance is you're just going to go and look it up. There's a bunch of tables. It depends on what you're dealing with. You just see what substance you're given in a problem, and then you can look it up. In the case of our homework, they're going to give you tables and values to use. But one that you should be familiar with is the specific heat of water. So this is just for liquid water, and in that case, it is 4.18 joules per gram Celsius. So if we multiply this by the mass in grams and the change in temperature in degrees Celsius, you can see those will cancel, and we're going to get out joules, which is an appropriate unit for energy or heat. So let's look at another example problem where we're kind of working backwards from the way that we did before. So a sample of meat containing only protein and fat has a caloric content of 372 calories. We would get that value from doing like calorimetry. The sample contains 21 grams of protein. This time I'm asking how many grams of fat does it contain? So we set up the problem just as we did before, only this time we don't have any carbohydrates. So the total energy is going to equal the mass of the protein times its caloric content plus the mass of the fat plus its caloric content. If I plug in the values from the problem, total energy released is going to be 372 calories from here. There's 21 grams of protein. I know its caloric content is 4 calories per gram. I'm asked for the mass of the fat, so that's my unknown. But I do know that its caloric content is going to be 9 calories per gram. If I subtract this term from both sides and move it over there, and then divide by 9 calories per gram, I'm going to get the mass of the fat all by itself. You can see here, this is that term minus this term, divided by that 9 calories per gram there. If I do this math here, I'm going to cancel these grams, and I'll see that 21 times 4 is 84. I'm left with calories, so now I have calories in the numerator, and I just have to figure out how to handle the units and do this division here. So I'm going to rewrite this to make that just a little bit more clear, because it's the first time we've seen that kind of mathematical form. So if I do 372 minus 84, I'm going to get 288 calories. I've written this like this, where I'm going to divide by, and I want to make it clear to everybody that when I write 9 calories per gram, this is really a fraction, right? I'm saying that there's 9 calories for every 1 gram, okay? And I would divide that. So when you divide by a fraction, that is going to be the same as multiplying by the reciprocal of that fraction, right? That is a rule that we learned from algebra. You are going to do the reciprocal, and you're going to do some multiplication here. Okay. Now I can see that I have calories down here, and I can cancel that with these calories here. And then the math I need to do is 288 divided by 9, and I get 32 grams of fat. You're going to see quite a few problems involving specific heat in our homework. So let's go through an example here. So say that I have a cup of tea with a mass of 101 grams, and it's heated from 24 degrees Celsius, so regular room temperature, to 96 degrees Celsius, just below boiling. How much heat is absorbed? That's my question. And we're going to assume a specific heat of 4.186 joules per gram degree Celsius. So we have our equation here where we have heat is going to equal the mass times the specific heat times the change in temperature. The mass that we have of the tea was given to us in the problem as 101 grams. It told us in the problem that our specific heat we're going to use is 4.186 joules per gram degree Celsius. And then we have our delta T, and we saw in a video previously that that would be the final temperature minus the initial temperature that we have. If we do this subtraction, we see that it rose 72 degrees Celsius. And if we do this multiplication through here, we see we cancel the degrees Celsius, we cancel the grams, we multiply 72 times 4.186 times 101, and we get 30,440 joules. We only have two significant figures here, so we can say that this is equal to 30 kilojoules. Finally, I want to talk about heating with phase changes. So, this is a graph called a heating curve, all right? And this one is for water. So what's going to happen is that, say I had ice and it's sitting well below 0 degrees Celsius, and I start applying heat. That ice is going to start to get warmer at a rate that is a little bit faster than liquid water would, actually, until it reaches a temperature of 0 degrees Celsius. At this point, it's going to stop getting warmer, but it is going to start to melt. It's going to start to change into liquid water. And not until all of the solid has turned over to liquid water will it start to rise in temperature again. So at this point, we now have a complete and total liquid, and it's rising at actually a slower rate than the ice did, all the way until we get to 100 degrees Celsius. At 100 degrees Celsius, it's going to start to boil. At that time, its temperature is going to remain the same while it turns into a gas until it's all a gas. Once it's a gas, it's going to start to heat up even faster than the liquid water did, up and up and up and up and up until we're off of the graph. So, there are different amounts of heat that are applied along this whole heating curve that I have bracketed out here. So the first one is the heat that was required to heat the ice. And we can see that this is our equation we've been using so far. It would be the mass of that ice, that water, times the specific heat of the water as a solid. So water is going to have a different specific heat when it's ice as compared to when it is a liquid, times the change in temperature, the difference between the point where it started and 0 degrees Celsius. Then we have the heat as it transitions from a solid to a liquid, the heat that was required along this plateau. Now, there is no change in temperature during this time, so we don't have that term. Instead, we have a different value that you would look up for each and every individual substance called the latent heat of fusion. It's a very fancy old-timey name, but it is just a number, and it is usually abbreviated like this, and you're just going to multiply that by the mass of water that transitioned from ice into a liquid, from a solid to a liquid. Then you have the heat of the liquid, and this is the exact same thing, only this time we're going to use the specific heat capacity of liquid water that we know is that 4.186 number, and then we would multiply it by the temperature difference between 0 degrees and 100 degrees when the liquid water was heating. And we could get that heat. Then we have the transition from liquid water to gas, and there's just another number to look up, and it's called the heat of vaporization, and we multiply that by the mass of water that was converted from a liquid into a gas, and we would get the heat of that process. And then finally, we have the exact same form that we had before, but this time there's a different specific heat capacity. This time it's a specific heat capacity for a gas. And that is how you would get all of the heat values associated with this process. Our example here was for water, but this actually holds true for pretty much any substance that's going to follow this path, unless, say, maybe there was a phase change directly from a solid to a gas or something. This would look a little different. But anything that, and most substances do this, but anything that turns from a solid to a liquid and then into a gas is going to be able to be broke down in this way. Their transition temperatures would be different in that case. The heat values will be different for it, but the way that we go about finding them is going to be the same.